Good morning, class. We are looking at exam 4 review covering chapters 4, 5, and 6 from 4.7 to 4.9, 5.1 to 5.5, and 6.1. We've already covered part 1. Here's part 2, which covers section 4.9 and 5.1. Let's get started. First, the anti-differentiation, also known as integration, there are formulas that we are supposed to know. And just as an example, if you have a constant and dx, which represents what is the independent variable, the answer is kx plus c. The power rule is the reverse process of the power rule for the differentiation, 1 over n plus 1 x to the power of n plus 1, and that works for every value of n except when it's -1, in which case we are really here. When it's -1, x to the power of -1 dx is the same as 1 over x dx, becomes a natural log. As far as constant multiple, sum and differences, it works just like a differentiation. You can do piece by piece. E to the power of kx, you divide by k, and e to the power of kx plus c. The derivative of sine is cosine, but the integral is negative cosine. The derivative of cosine is negative sine, but the integral is positive sine, so on and so forth. So these are some integration formulas. Hopefully we are comfortable with them, and we are going to move on, starting with the of course, we will have FTC. We will discuss the FTC, or the fundamental theorem of calculus, which says differentiation and integration, they undo each other. And also, if you want to evaluate the definite integral of a to b f of x dx, is capital F of b minus f of a. We'll discuss that as we come across the examples, but this is the synopsis of the integration. And so with that being the case, we also have what's called the substitution rule, which is the reverse process of the chain rule. All of them will be discussed. So for now, we want to find all functions g such that g prime is 4 sine x plus 2x to the power of 5 minus square root of x over x. And I'll put some of the formulas for you here, just so we will use that again. If you have a constant, it's kx plus c, x to the power of n is 1 over n plus 1, x to the power of n plus 1 plus a constant. This is called the power rule. E to the power of kx, 1 over k to the power of kx plus c, 1 over x gives you natural log. A cosine gives you sine, and sine gives you negative cosine. On all of them, we add a constant, simply because the derivative of any number is 0 and makes no difference. So what is the solution? Sometimes you will need to simplify first. Factor, cancel, remove radical notation, etc. Sometimes you will need to integrate using substitution. So the very first thing happens here, we make up two fractions, which means we have this one and then this one, where square root of x is x to the power of 1/2. This is x to the power of 1. And we can simplify them as such. Therefore, we can use the power rule on the last two pieces. So we want to integrate this. And to integrate this, we can use the elongated sign as the Leibniz used, along with dx. So g of x is the integral of the right side times dx. Pay attention that this tells us what is the independent variable. So we are going to do this step by step. 4 sine x. Again, the derivative of sine is cosine, but the integral is negative cosine. So that gives us 4 times negative cosine, or minus 4 cosine x. This one, 2x to the power of 4, we are going to use the power rule. 2 we are going to add 1 to this and divide by 2 divided by 5x to the power of 5. We do exactly the same thing here, minus. We add 1 to this number, okay? We divide by it and we raise it to that power. So 1 over negative 1/2 plus 1x to the power of negative 1/2 plus 1, we keep the negative sign. So what happens? This is 1/2. The reciprocal of that is 2. And this is x to the power of 1/2, as you know, square root of x. And that's the final answer, everybody. So very straightforward. I hope everybody is comfortable with that. We are practicing. There's 2 more, and we are going to integrate, obviously, all of them in this case are using, in essence, the power rule. So let's do that. So we are mainly concerned with this. We add 1, becomes 5, we divide by it. So 2 over 5, x to the power of 5. This one, we add 1, becomes 4. 3 over 4, x to the power of 4. This one, we add 1, so minus 7 third x cubed. I hope you realize when x doesn't have an exponent, the exponent is 1. So when you add 1 becomes 2, so 1/2 x squared and minus 5x. And pay attention to the fact that whatever this one is, and of course all of them must have the same, this is dx, which tells us x is the independent variable. In this case, it's easier to square it first. A minus b squared is a squared minus 2ab plus b squared. Just quick reminder. So we get x squared minus 10x plus 25. And now this becomes 1/3 x cubed. This becomes minus 10 divided by 2x squared, or minus 5x squared. And this becomes 25x, and we are done. Needless to say, this is the integration, also known as indefinite integral. So you add a constant because this gives you a general solution, a family of functions. All right. Whether we want to differentiate or integrate, the first step is algebra, and that means make up 3 fractions. This one gives us 1. This one minus 7 over x. This one 2 over x squared. So we make up 3 fractions. We know how to differentiate this. We get simply x because the independent variable is x. So x. Now I'm going to rewrite this as minus 7 times 1 over x, so it becomes clear the answer is a natural log. And I'm going to write this as 2x to the power of negative 2. So this one is x, clear. This one is minus 7 ln x. Again, do you have to write it as such? No, but if it helps, you must, because 1 over x, clearly the answer is natural log of the absolute value of x. And by the way, the absolute value, because the domain of a natural log is 0 to infinity, positive values. 0 is not included. And this one, I want to quickly show you how to integrate. So 2 divided by negative 2 plus 1, x to the power of negative 2 plus 1. Negative 2 plus 1 becomes negative 1 So you get negative 2x to the power of minus 1, which is negative 2 over x. And so the final answer is x for the first one, minus 7 times ln of absolute value of x for the second one, and minus 2 x to the power of minus 1 means minus 2 over x and a constant for the 2 over x. Want to integrate this, pay attention to the fact your independent variable is t because we have dt. Therefore, the answer to 1 is not x, it's t. Cosine, the derivative is negative sign, but the integral is positive sign. So the integral is positive sign. So pay attention to this one. So t plus sine t, and we add a constant. T plus sine t, and we add a constant. All right, to integrate this, first we need to do an algebraic technique and change this to a format that can use the power rule, x to the power of 1/3. So this one, 1 over 1/3 plus 1, x to the power of 1/3 plus 1. Minus sine x. Remember, the derivative of sine is cosine, but the integral of sine is negative cosine. So minus negative cosine and a constant. So we are here, minus negative cosine and a constant. Well, obviously this becomes plus, but what happens to this one? Four-thirds is 3/4. This one you can leave it like that, or you write it as 3/4 cube root of x to the power of 4 plus cosine x plus a constant. All right, we are moving on with more and more integration. And again, the technique that has been discussed, you make up two fractions, x divided by square root of x and 1 over square root of x. Needless to say, by now everybody knows square root of x is x to the power of 1/2. And the reason we do that is so when we divide this, becomes a format that power rule can be used. This is x to the power of 1/2. Just in case, I want to make sure that everybody remembers that a to the power of m over a to the power of n is a to the power of m minus, and that's what we are using here, okay, the quotient rule for exponentials. And so this is x to the power of 1/2 because the exponent here is 1. Let me just write that for you. So the exponent here is 1. And this one becomes x to the power of negative 1/2. Now we are ready to use the power rule in both cases. So this one, 1 over 1/2 plus 1, x to the power of 1/2 plus 1. Plus this one, 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1. And since there is nothing else, we add a constant. And as you can see, this is the only calculus step, and we're done, class. So let me actually put an asterisk next to it because it is important. This is the only calculus step. We're done. Everything else is algebra. 1/2 and 1, they add up to 3/2. Negative 1/2 and 1, they add up to 1/2. You're dividing by 3/2 becomes 2/3. You're dividing by 1/2 becomes 2, the reciprocal. And we are done. And please understand, this was the only calculus step. Algebra, 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 algebra. Meaning, prior knowledge of mathematics is that important. We want to integrate this, and first this part, we make up two fractions. This one is 1, this one is 2 over x squared, and since this is the x, this becomes x. This one we have done that, if you recall, from the previous page. 2 over x squared ended up being minus 2 over x, but I quickly remind you again. So for this one, you would write 2x to the power of minus 2, okay? And if you want to integrate that one, you say 2 over negative 2 plus 1 x to the power of negative 2 plus 1. That's why you get minus 2 over x. And if you remember, the derivative of tangent is secant squared. Therefore, the answer is tan x and a constant for the last part. The derivative of tan is secant squared. The derivative of tangent is secant squared. Therefore, the integral of secant squared is tan x. All right, so the initial value problem. In this case, in short, we are given the same integration anti-differentiation, but they have added a pair. So this means zero comma 1. So it's called an initial value problem because now with the help of that, we can find the constant. So any equation containing a derivative is called differential equation. So whatever we've done so far, it's a differential equation. A function which satisfies the equation is called a solution to the differential equation. An initial value problem is a differential equation along with a specified value of the unknown, a pair, called the initial condition. So the point is that can help us figure out the constant. So first, this means dp is the product of these two. And if I integrate both sides, by the way, it's very important to know, you can't integrate this without the dt. If the dt is missing, it is wrong. It may be a typo, but there has to be a dt always. So this becomes p of t, and this one we are going to integrate. And as you know, when we differentiate, we multiply by 3. When we integrate, we divide by 3. So this becomes 2 divided by 3 e to the power of 3t and a constant. And be very careful with that. Again, in the case of differentiation, we multiplied by 3. In the case of integration, we're going to divide. And at this point, if you differentiate, you get this one back without the dt. What you're looking at is the indefinite integral, also known as a general solution. Now, if we didn't have this pair, we would be done, just like previous pages. Since we have this pair, now we have an opportunity to find c. So we plug in the pair, meaning we replace the t with 0, and then the p of 0, or the result, with 1. As you know, e to the power of 3 times 0 is e to the power of 0, which is 1. So we get 2/3 plus c equals 1. C becomes 1/3, and you replace the constant with that, and now you have one solution is called a particular solution. So in other words, we have a general solution, we have a family of functions, we have infinitely many solutions, because if you recall, if you graph y equals 2/3 e to the power of 3t, plus c takes it up and down depending on the value of c along the y-axis. But now we know exactly what c is with the help of one pair. So this is a general solution, this is a particular solution. It's one specific solution. We have another one we want to solve. So first and foremost, recognize that this one is giving us the pair when 1, 5. And so we are going to integrate dy. So we are going to multiply both sides by dx. And if we integrate, this one becomes y. And this one we are going to integrate, okay? And to integrate, we know 1/x is a natural log, so we are going to change square root of x to x to the power of 1/2 and bring it up, make it negative 1/2. So we get it ready for the power rule. So the first part is obviously natural log. But what about this one? We are going to use the power rule, 1/negative 1/2 plus 1, x to the power of negative 1/2 plus 1. And again, we've seen this, there is nothing else there, we add a constant. This is positive 1/2. So this make it positive 2 square root of x. And again, what you're looking at, it's called general solution. Let's plug in the pair, replace the x with 1 and y with 5 to see what is the constant. As you know, ln1 is 0. This is 1. So 2 plus c equals 5. C becomes 3. And we are going to replace it. And what you're looking at now is a particular solution. Again, meaning one specific solution, not a family of functions. This is a family of functions, infinitely many, even known as indefinite integral when we end up with a constant. Now the constant is known with the help of one pair, that is a specific solution. Rectilinear motion. A particle moves in a straight line and has acceleration given by s of t equals 60 plus 4. This is A. Acceleration is given by A. 60 plus 4. Its initial velocity, v of 0, is -6 centimeters per second, and its initial displacement, s of 0, is 9. We want to find its position function, s of t. So first of all, reminding everybody what we learned in physics, a rectilinear motion, or motion in a straight line with constant acceleration a, initial velocity v sub 0, and initial displacement s sub 0, the displacement after time t is given as s of t equals 1/2 at squared plus v0 t plus s sub 0. That would be if we happen to have a constant acceleration motion in a straight line. But in general, what we are looking at is the reverse process of differentiation. When you have a position function, when you differentiate it, it gives you the velocity function. When you differentiate the velocity function, gives you the acceleration function. Now we have the acceleration and we want to go to the position function. To do that, if v prime or a of t is given as 6t plus 4, then we want to integrate this or anti-differentiate this to find the v of t. And by now, we know again, so the anti-differentiation, 6 divided by 2, 3t squared plus 4t plus a constant. So we can do this. Okay, and so we get that. So what is the problem? The problem is a constant. However, we are given the initial value 0, comma negative 6. That means when t is 0, the v is negative 6. So if you plug in 0 in here, everything goes to 0. So v of 0 becomes c, which is negative 6. So v of 0, if I plug in 0, I get c. On the other hand, v of 0 is negative 6, so c must be that. And so if that is the case, v of t, I can replace the c, and that's the velocity function. So this is a of t, acceleration function, results in v of t in general. And since we have the initial velocity, we end up with the velocity function. Now, if we integrate this, again, integrate this. By the way, when you integrate, you have it, remember t here. Okay, so if you integrate this, this becomes s of t. This becomes 3 over 3 t cubed plus 4 over 2, 2t squared minus 6t plus another constant. So you can say c sub 1 and now c sub 2, or you can say d. The point being, I don't want to use the same c here because I don't want anybody to be under the assumption it's the same constant. That's why we are using something else. You can say c sub 1 here and c sub 2 here. If you use a c and understand it's not the same, it's okay, but it's really awkward. Don't take a chance. We know s of 0 is 9. So if I place t equals 0 here, s of 0 is d, and s of 0 is 9. Okay, if I plug in 0, I get 9. Also, I get s of 0. If I plug in 0, I get d. So d must be 9, and this is the position function. That's what we were looking for. And now, you should always check your work. S of t is t cubed plus 2t squared minus 6t plus 9. If I differentiate this, I get 3t squared plus 4t minus 6. Okay. If I differentiate this, I get 6t plus 4. So differentiate it and do it again. It should give you a of t. This is a of t. Back. And that's how you check your work. A sample of cesium-137 with an initial mass of 79 milligrams decays t years later at a rate, this is the rate, of negative 1.8249 e to the power of negative 0.0231 t milligrams per year. Pay attention to this. Find the mass after 23 years, and they want us to round it to 1 decimal. Well, since this is the rate, and we're talking about the mass. This is the rate of the mass. So if we let m of a t represent the mass of cesium-137, cesium-137 is a radioactive substance. 2 years later, then m prime of t or dm dt. The difference is when we write dm dt, it's more precise in the sense that we know the independent variable is t. So dm prime of t or dm dt is what they gave us here. This is the derivative function. The concept of a rate means the derivative function. So here's dm dt. And the initial value, m of 0 is 79. So we're going to find m of t through the process of integration. And then we want 23 years later, we plug in 23. That is the translation of the question. First, we define our variable m of t, and then we write what's given. So m of t is the integral of this times dt. So dm is this times dt. So m of t is the integral of the right side times dt. As you know, if we are differentiating, we multiply by this coefficient of t, but we are integrating, we are going to divide. So we're going to divide this number by this and add a constant. And we write the same thing. So I'm looking at this. When we divide, it becomes, and again, you can put it into a calculator, it becomes 79. And m of 0 is 79. So if I put here 79 and I replace this with 0, m of 0 is 79. That means 79 equals 79 e to the power of 0 plus c. That's the meaning of it. As you know, e to the power of 0 is 1. So 79 plus c equals 79, c becomes 0. And this formula, basically, you rewrite it without the c. So this is m of t. We want 23 years later, m of 23, replace the t with 23. Put it into a calculator with a bunch of decimals, and then it says 1. Now you use 1. By the way, it's very important that your intermediate steps are pretty precise. Eventually, you do 1 decimal. In other words, you don't want to go with 1 decimal anywhere in between, okay? So that's important to accept the last step. If you do that, it messes everything up. So that's the concept of anti-differentiation, integration. And now let's look at integrals, which is chapter 5 and 5.1, areas and distances. So suppose a continuous function f is defined on the interval of a to b, closed interval of a to b. So we have a continuous function. If the interval is divided into n subintervals, so that delta x is b minus a over n, this is the width. X sub 0 is a, x sub 1 is a plus delta x, x sub 2 is a plus 2 delta x, and the last one, b, is a plus n delta x, or x sub n. Then a Riemann sum associated with f is the summation of I from 1 to n, f of x sub I delta x. For example, f of x sub 1 delta x all the way to f of x sub n delta x. X sub I is any point in between, can be the left end points, the right end points, or anywhere in between. I hope everybody remembers this concept. We are going to make some sense out of this. And so the concept is a geometry and a procedure called Riemann sum or summation. We partition the interval of A to B into a few. Let's say we make up 4 subintervals and we make 4 rectangles. The width would be B minus A divided by 4. And the height would be f of x sub 1, f of x sub 2, f of x sub 3, f of x sub. Then we come up with more than 4, for example, 8. As the number of rectangles increase, the approximation gets better. So the idea is this, everybody. If you want the area under the curve, let's say from A to B, you can cut this into so many pieces. Let's see. Okay, and this width is B minus A over N. In this case, I'm choosing N to be 4. It doesn't have to be, but I'm saying in general. So the width is fixed. That's your delta X, everybody. What is the height? Well, I can use the left endpoints. And use this one as the height. That means f of x sub 0 or f of a and the rest of it. I can use the right endpoints. I can use the midpoint, or I can use any point in between. The point is we can add them up and it gives us an approximation. And this approximation gets better as we add to the number of rectangles. That's the concept. Now, left endpoints rule, right endpoints, left endpoint rule, right endpoint, and midpoint. L for left, R for right, M for midpoint, delta is x times f of x sub 0 to all the way to n minus 1, or n x sub 1 to x sub n, and this is the midpoint. Again, I make it nice and easy with a simple example in a moment. Conceptually is really very simple. So the area is approximated under the curve as summation of f of x by delta x are going from 1 to 4, for example. You follow what I'm saying? If we cut it into 4 pieces. And the area under the curve is exactly equal to that if we take the limit of this Riemann sum, look at this Riemann sum, and we let n go to infinity, where delta x is b minus a over n, x of I is a plus I delta x. This one is only 4 pieces, okay, which is definitely an approximation. Let's really make some sense out of this with a simple example. We are interested in to approximate this integral by using the left endpoints, right endpoints, midpoints rule with n equals 5 to approximate the integral. The integral represents the area under the curve if it's a positive function. And I have L sub n, R sub n, M sub n, so on and so forth. And I want to show you an easy way you don't have to memorize the formulas. Okay, so what we want to do to get this started, please understand that we have the function y, or f of x is 1 over x. A is 1, B is 2. So from 1 to 2, lower limit to upper limit. Here's the graph of a y, or f of x equals 1 over x. So f of x is 1 over x. A is 1, b is 2. So here's number 1, here's number 2. So we are interested in this area. This, if I shade this area, this is what we want. Again, see. This is what we are interested in finding. As you know, we don't have a geometric shape and therefore a geometric formula for the area. So that's why this approximation takes place with the Riemann sum. Now, delta x is b minus a over n, 2 minus 1 over 5, which makes it 1/5 or 0.2. Now, I'm going to show you a very easy way to handle this. The concept is the delta x, when you're going to cut from 1 to 2 into 5 equal parts. Five equal parts, starting with 1, and then add 1 over 5 or 0.2. So I'm going to blow up 1 to 2 to make it huge, so everybody can see this is 1, this is 2, okay, and I'm adding 1/5 or 0.2, 1.2, 1.4, 1.6, 1.82. So from here to here, draw a line segment, make it large enough so you can clearly see. And A is the left end point, B is the right end, okay? And in between, just add whatever this number you got. So what happens is that you're cutting this into 1, 2, 3, 4, 5 pieces. What is the width? Delta x is fixed at 0.2. Doesn't have to be, but it makes it easier. But let's go with these points. Rather than memorization, delta x is clear. Now, what is the formula? 1 over x, right? We are going to put the left endpoints. When you put the left endpoint, that means that gives you the height. If I plug in 1, I'm talking about this height, everybody, this height. So I plug in 1 here. Then 1.2 is somewhere in between that height. And for the left end points, because it says left, I have 1, 2, 3, 4, 5. There are 6 points. I don't use the b for left end points. That's the meaning of f of x sub 0. X sub 0 is a, x sub n for this one is b. So use all of this except b for the left end points. See, the function is 1 over x, 1 over 1, 1 over 1.2, 1 over 1.4, 1 over 1.6, 1 over 1.8. And I'm going to assume everybody can put it into a calculator and do it with a bunch of decimals. How many decimals? Normally they tell you. If they don't, put many, 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 many decimals. I can't emphasize this enough. Now, I want to do the right endpoints. See, again, there are 6, so don't use the first one. Use all of them. See, we use the first one for the left endpoints. When we say right endpoints, then you don't use this one. You use everything, including the 2 at the end. So take a look at what happens for the right endpoints. So I don't start with this one. I start with this one. I go to 1 over 8, and this is b. This 2 is b, everybody, the last one. And as far as calculation, even if you do it by hand, it's fairly simple because this and this are identical, okay? So this will help you find both of them. One of them is maybe tedious, the other one is easy. Okay, so you have the answer and you're done with that. Now, what about the midpoints? And pay attention to this. What does this say? The midpoint says f of x of 1 bar. That means in between. Are you with me? So all you have to do, calculate just one of them. That means add this 2, divide by 2, and this becomes 1.1. one. Take a look. Let me grab a different color here. This point is in between, and it's 1.1. Then the next one is 1.3. You add the same delta x here. Here's the next one. Here's the next one. Keep on adding 0.2. So 1.5, 1.7, 1.9. So M5, or the integral of 1 over x dx from 1 to 2 is this is an approximation. Again, same thing for here, it is an approximation. F of 1.1 delta x times f of 1.1, 1.3, and so forth, which means 1/5. So this one I'm showing you with all the details. So this is 1 over 5th. This is 1 over 1.1. Why is it 1 over 1.1? Because that's your function, 1 over x. Let's say it was x squared, you would say 1.1 squared. And again, use a calculator and you come up with the answer. And generally speaking, the midpoint is a better approximation. In fact, if you look at the midpoint, is always between the two. So let me quickly recap, because I don't want you to have any difficulty calculating this, because it does take some time. So first and foremost, you find out what is your function. Then you look at the limits. The lower limit is a, the upper limit is b. Then you graph the function. You calculate the delta xb minus a over n. And wherever, in this case, you want to go from 1 to 2, you blow it up, you make it huge, so it becomes very easy. Just a line segment from 1a to 2b. So from 2. So you always write from a to b. It happened to be 1 and 2, could be any other number. But notice we make this large enough so it's easy to cut it into however many pieces. Okay. All right, the velocity of a moving object is given by the function v of x equals 3x, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled during the first 3 hours. So v of x equals 3x, or y equals 3x. I hope you know that it's a line that goes through the origin and has a slope of 3. I'm going to assume everybody can graph this. It's a very simple 0, 0. And then if you, just for the sake of argument, if you plug in x equals 1, becomes 3. So this would be 1, 3. So you can draw this. And because we are dealing with velocity and time, we don't have it on a negative side. Okay, so during the first 3 hours, that means we want this area. Antiderivatives as areas, okay? So how do you find this area? Area is 1/2 base times the height. And we notice this point has coordinates 3. And then if you plug in here, it's 9, right? This one has coordinates 3 and 9. And this is not to scale by any means. So this is a right triangle. So the base is 3. So the height is 9. This distance is 9. Everybody, let me, again, by no means this is to scale. This is 9. Okay. So just plug in 1/2 base, which is 3, height, which is 9. And it's 27 divided by 2, or 13.5 miles in this case. This is miles per hour, and that's how you know the units are in miles, okay? What about between the 3rd and the 5th? third and the fifth, you do the drawing, third and the fifth, and you want this area. As you know, this is a trapezoid. This is a trapezoid. An area of a trapezoid is 1/2 the height times smaller base plus the larger base, or B1 plus B2. So I hope you recognize this is the height, this is the H, which is 5 minus 3 or 2. This is H, everybody. This is H. This is B1. This is B2. So 1/2. The height is 5 minus 3 or 2. Smaller base, if you should know it's 9, or just if you plug in 3 here, you get 9. And 5, if you plug in, you get 15, or you can say 9 and 6, and which is 15. And so 2 cancels out the 2, and the answer is 24 miles. By the way, you can calculate the area of this rectangle and the area of this triangle and add them up, but that's up to you. Just the trapezoid will do the job. Use the definition to find an expression for the area under the graph of f as a limit. Do not evaluate the limit. F of x is x squared plus the square root of 1 plus 2x. X goes between 4 and 7. Find delta x and x sub I. So the area under the curve, when the function is continuous and positive, is the limit of summation of I from 1 to n f of x sub I delta x as n goes to infinity, where delta x is b minus a over n, x sub I is a plus I delta x, and delta x is b minus a over n. So according to this, we are going to go from 4 to 7. So a is 4, b is 7. And since delta x is b minus a over n, so 7 minus 4 over n, or 3 over n. So I'm looking at this one. Okay, everybody? I'm looking at this one. Now I want x sub I. X sub I is a plus I delta x. A plus I delta x. A is 4. I, we found delta x to be 3 over n. So I times 3 over n, or 3i over n. So that's x sub I. We are going to use this limit as the area, right? I'm going to use this limit. We can call it, by the way, this is when we go with this method of a plus I delta x, it becomes the right endpoints. Normally we use the right endpoints, but it doesn't matter, like I said, because n goes to infinity, left endpoints, midpoints give you the answer. For the sake of a limit, because we're going to discover this a little bit, explore this a little bit more later on, we normally use R sub n. So let's plug in. We need to figure out f of x sub I, because we already know delta x. Okay, so that's not a problem. Is it? So if I want to plug in here, delta x is 3 over n, but what is f of x sub I? So first, x sub I is this, and f of x is this. Okay, x sub I, we found it to be a plus I delta x over 4 plus 3i over n, and f of x is given, right? So if I want f of x sub I, that means I'm going to replace the x with this. You follow what I'm saying? F of x sub I. I'm going to replace this one with this. I get 4 plus 3i over n to the power of 2 plus square root of 1 plus 2 times this. That's f of x sub I. Please understand what we are doing here. Here's x sub I, here's f of x, and therefore here's f of x sub I. Replace anywhere you see x with x sub I. 4 plus 3i over n, 4 plus 3i over n. And of course, we don't have to simplify it here. Eventually, this can be evaluated. If I want this one now, I'm going to tag along delta x. So a is the limit as n goes to infinity of summation I going from 1 to n. I put this one here and I replace the delta x with 3 over n. And they don't want us to evaluate. But it is important to be able to come up with this. This is actually the main part, and then it becomes fairly simple to find the limits. So, given a function, given the limit of a to b, we can find and set up the area. Of course, this is not a finished job. We have to find its limit. So that's one way to look at this question. Another one is we want to determine a region whose area is equal to the given limit. Do not evaluate the limit. So what they are saying is previously they gave us a function and a and b. So go back. They gave us a function and a and b. Okay. Now, and we came up with this limit. Now, if they give us the limit, can we come up with the function and a and b? That's the idea. Okay. So let's see what we have here. Again, we are going to write a is the limit of R7 as n goes to infinity equals to that. So we're going to compare these two. And you notice 3 over n is delta x. And f of x sub I is what you have here. So compare and figure things out. Now, we know that delta x is b minus a over n, and x sub I is a plus I delta x. We know this, right? Delta x is b minus a over n, and x sub I is a plus I delta x. We know that. And we also know delta x is 3 over n. X sub I could be the whole thing here. Again, this is one way to look at it. So this is clearly 3 over n, and this is 1 plus 3i over n. This is 3 over n. This is 1 plus I, 3 over n. Now, if we assume a equals 1, so if you replace the a with 1, where b minus a becomes 3, b becomes what? B must be 4. So one way to approach this is to let y or f of x be square root of x in the interval of 1 to 4. Again, pay attention to a plus I delta x. We are choosing a to be 1. Now, this is not unique because we don't have to really choose a to be 1. We can actually choose it to be any number. You can even pick 0. So if you do that, what happens? Let me show you another example. So delta x is fixed at 3 over n. You can't change that. But x sub I, if we go with this route, we are choosing a equals 1. May not be. But if it's 0, if a is 0, and this is b minus a, and a is 0, then b must be 3. B must be 3. Which means this is 0 to 3, but what happens to this one? It requires that 1, remember that? So it's the square root of 1 plus x. So we can say y is f of x equals square root of 1 plus x on the interval of 0 to 3. And that was what makes it interesting. This is not unique. You can go this route with a different limits, or this route 1 and 4. Which one is easier? You choose, both of them are just as good.